Have you ever opened an engineering drawing like this and wondered, where do I even start? There are dimensions everywhere, symbols you have never seen before, sections, detail views, GD&T, datums, whole callouts, tolerances. At first glance, it looks impossible. But here's the truth. Professional design engineers don't read this drawing from left to right. They follow a systematic process. And once you learn that process, even complex drawing becomes surprisingly easy. In the next few minutes, I will explain every important part of this drawing exactly the way experienced design engineers read it. Let's begin. Every engineering drawing begins with the title block, which is this. Many beginners skip this section. Experienced engineers never do. So let's see why. The first thing we find is the part name. This part name indicates the type of the part that we are actually seeing. Here it is central link. Immediately we understand that this part is likely used as a connecting member inside a mechanical assembly. Next comes the part number. This part number is a unique number which allows manufacturing, purchasing, and quality departments to identify exactly which component is being discussed. Notice that the material specified is alloy steel. This immediately tells the manufacturing engineer that machining parameters, heat treatment, and inspection methods will differ from those used for aluminum or plastic. We also find the sheet number and the total number of sheets that are part of this drawing. Here we have 1 sheets in total, and this is the sheet number 1. We also have the name of the person who has drawn this drawing and the name of the person who has checked, and then the name of the person who has approved this drawing. These fields establish complete document control and traceability. Also, we have the issue date. And here we have the next assembly into which this part will get assembled. Here we have a scale which specifies what is the type of scaling that we are using in this drawing. It is NTS, that means not to scale. Otherwise, here instead of NTS, there may be other scaling options like 1:1, 1:2, 2:1, depending on the part. Here we have a very important symbol, which is the orthographic projection symbol. This symbol is for first angle projection. So, the drawing that we are seeing here can be interpreted by using this first angle projection. Next, let's find the main view. In this drawing and in every drawing, the front view is always considered the main view, which will contain maximum number of dimensions. Here, this is the front view because this contains maximum number of dimensions and all the other views are generated from this base view. So, let us analyze this front view. Here, as soon as I see this front view, we see one circular boss with a center hole and 2 arms here. The arms are having forked ends. You can see we have a fork end here and another fork end we are having here. And of course, there are several holes here. This center boss acts as a primary reference for many dimensions. The arm transfers loads and the fork end will probably connect to another pin or linkage. Instead of randomly dimensioning every feature, the designer organizes dimensions from important reference locations. That makes manufacturing much easier. Now let's understand dimensions. There are different types of dimensions in this drawing. If you see here, these are linear dimensions. And if you see, these are diameter symbols. to specify the diameter of holes or circular features. This is radius dimension specified by R, and this TYP indicates it's typical. That means the same type feature like here we have will possess the dimension as R15. Next, if you come here, these are angular dimensions. See, angular dimensions 36 degrees, and all the dimensions are having tolerances. If you see here, this radius 15 is having a tolerance of plus 1.0, and here this diameter is having a tolerance of 0.1 in the minus side. So the dimension will vary from 20.1 to 20.2. And here if you see, this is the angle tolerance plus minus 15 minutes. And if you come here, this center to center location is 20 plus minus 0.3. So it will vary from 19.7 to 20.3. Tolerances are very important, which specifies the allowable manufacturing variation. Without tolerances, manufacturing would not be possible. Now here there are many standard callouts like I told you about TYP. Let's analyze the standard callouts. Here we have through hole dia 5.2 that indicates here there is a hole and it is through hole, that is it passes through the body of this part. Here also we have a through hole, and as we move down here, this is dia 5 3 holes that indicates there are 3 holes and to each hole the diameter is 5. So we need not give the dimension to this other 2 holes. Now let's have a look at this view. Here if you see, all the dimensions are completely defined. The slot width, the total width, the angular orientation, everything is completely defined. In every drawing, the dimensions will be specified some or the other way in any of the views. This is the difference between a fresher and a experienced engineer, the way they find out the dimensions. Suppose if we want to find the dimension of this arc, maybe we want the radius. So to find this radius, if you see here, the dimension is not given. But if you move to another view, see, this is the detail I. If you see here, this detail I view will contain all the dimensions. But here also, if you see, directly this radius is not given. So how to find it? If you see here, this is 6 and this 6 is the diameter of this circle or arc. So the radius would be 3 mm. So this is how you can find the dimensions which are not given directly. Now let's look at the section views. Here this is a section view. Now this view is generated from this section line, that is section AA. And if you see here, this section AA is written here. This is called a full sectional view. This entire object is cut through this plane and this upper portion is removed and the view is shown from the top for this lower portion, and the view will be like this. You can see for these holes, after we have generated the section view, the entire thing is cut. That indicates these are through holes. Now I had told you here we have through hole already specified. That means there is a hole here which is completely through. But for these holes, nothing is mentioned. The depth is not mentioned. But if you see this section view, we can understand that this dia 5 holes are completely through. Now there is another section, section EE. The object is cut in the orientation EE And as the arrow is upwards, so this bottom section is removed and this top section is viewed in this direction, that is in the direction of this arrow. And when you come down here, this is the section EE, which exposes all the internal features of this arm. Here we have 3 holes, diaphragm, and they are through holes. Also, you can see the position of the holes here. Without this section view, many internal features will be hidden, and we cannot show them by use of direct solid objects. Section views reduce ambiguity and greatly improve manufacturing accuracy. Now, there are some areas like this one which is very small if you compare with this sheet, and there are many dimensions. So, instead of crowding the drawing, engineers create detail views. Here we have detail I, and this detail I view is shown here, which is an enlarged view, and you can see the scaling. It is 4:1. That means this particular region is scaled 4 times. That is, it is enlarged 4 times and it is shown here so that we can see each dimension clearly. See, every dimension is visible clearly. Now imagine all these dimensions if we put here, how crowded it will be. Similarly, here also we have a detail view, that is detail J. This is for this area. Here, this detail J is this, which contains all the dimensions of the fork on the second side. This enlarged view shows small radius, slot dimensions, chamfers, and feature relationships that would otherwise be difficult to read. Whenever you see a circular boundary with a label, that indicates it's a detail view. And you can find the detail view elsewhere on the sheet with the dimensions. Now we have arrived to one of the important parts of modern engineering drawing, geometrical dimensioning and tolerancing, GD&T. Notice these rectangular symbols. These are called feature control frames. Inside them, we find symbols representing position, parallelism, angularity, flatness, concentricity, and other geometrical controls. We also see references like here we have datum G, datum D, datum C. These are all called datums. Datums establish the reference coordinate system used during inspection. Instead of checking every dimension independently, quality inspectors first establish the datums. Then they measure all control features relative to those references. This produces much higher manufacturing consistency, especially for precision mechanical assemblies. Now look at this drawing one more time. A few minutes ago, it probably looked overwhelming, but now you know how professional engineers approach it. Start with the title block, then go to the main view and understand it, interpret the dimensions, study the holes, slots, read the section views, find the orientation of the section, understand the section views, find the detail views, and go to the detail view representation area, examine the details, finally interpret the GD&T and datum references. That's exactly how experienced design engineers decode complex manufacturing drawings. If you want to master engineering drawings from beginner to professional level, subscribe to this channel, because in the next videos we will explain real production drawings, GD&T, limits and fits, surface finish, manufacturing tolerances, and complete drawing interpretation used in the industry. In the next video, we are going to interpret the GD&T symbols that are present in this drawing. So stay tuned. I will see you in the next video.